Space is vast and full of wonders. It's a realm that stretches beyond our imagination, filled with countless mysteries and phenomena that continue to baffle and inspire scientists and dreamers alike. It's a place of incredible beauty, where galaxies swirl in a cosmic dance and nebulae glow with vibrant colors, painting the universe with their ethereal light. But it's also a place of immense power, where forces beyond our comprehension shape the very fabric of reality. Stars are born in fiery explosions, and they live out their lives in a delicate balance of nuclear fusion and gravitational pull. Stars are born, they live, and they die. Some deaths are quiet, fading into the darkness. Others are incredibly violent, ending in spectacular supernova explosions that outshine entire galaxies for a brief moment. Today, we're going to talk about one star that survived a cosmic explosion. This star didn't just fade away or explode into oblivion. Instead, it defied the odds and continued its journey through the cosmos. Meet LP40 365, a star that refused to die. This remarkable star is a testament to the resilience and unpredictability of the universe. It's a survivor, a testament to the universe's awesome power. LP40 365 is not just any star, it's a symbol of survival and endurance in the face of unimaginable forces. This isn't just any star, it's a special kind of star called a white dwarf, the remnants of a star that has exhausted its nuclear fuel and shed its outer layers. White dwarfs are fascinating objects, incredibly dense and hot, shining with the residual heat of their former lives. But LP40 365 is even more extraordinary, and its story is one of survival against incredible odds. Imagine a star that exploded, tearing itself apart in a cataclysmic event. Imagine a star that exploded, tearing itself apart. The explosion should have been the end, but for LP40 365, it was just the beginning of a new chapter. Now imagine a fragment of that star still burning bright, hurtling through space. That's LP40 365. This fragment, against all odds, continues to shine and move through the cosmos, a beacon of resilience. It's a zombie star, a survivor of a supernova. LP40 365 is a reminder of the incredible power and mystery of the universe, a star that refused to be extinguished. To understand LP40 365, we need to talk about white dwarfs. These fascinating objects are the remnants of stars that were once similar to our own sun. They represent the final evolutionary stage of these stars, and studying them can give us incredible insights into the life cycles of stars and the future of our own solar system. These are the remnants of stars like our sun. When a star like the sun exhausts its nuclear fuel, it undergoes a dramatic transformation. The outer layers are expelled, and the core that remains is what we call a white dwarf. When these stars run out of fuel, they collapse in on themselves. This collapse is a spectacular event, leading to the shedding of the outer layers and leaving behind a dense core. This core is incredibly compact and is composed mostly of carbon and oxygen. What's left is a dense core, about the size of Earth. Despite its small size, a white dwarf contains roughly the same mass as the sun, making it an object of extreme density. This core is incredibly hot and incredibly dense. The temperatures on the surface of a white dwarf can reach up to 100,000 degrees Celsius, which is much hotter than the surface of our sun. A teaspoonful of white dwarf material would weigh as much as an elephant. This is because the matter inside a white dwarf is packed so tightly that it defies our everyday understanding of density. That's how tightly packed the matter is. The electrons in the atoms are squeezed together, creating a state of matter known as degenerate matter, which is incredibly dense and stable. White dwarfs are like the embers of a dying fire. Over time, they slowly cool down, losing their heat and fading away. This cooling process takes billions of years. They slowly cool down over billions of years. As they cool, they transition from a bright, hot object to a faint, cool one. Eventually, they will become black dwarfs, although the universe is not old enough for any black dwarfs to exist yet. They don't produce new energy. Unlike stars that burn through nuclear fusion, white dwarfs have no source of new energy. They simply radiate away the heat they have left. They just radiate away their leftover heat. This radiation is what makes them visible to us, even though they are no longer undergoing fusion reactions. But even though they're cooling, they're still incredibly hot. The surface temperatures remain high for a long time, making them fascinating objects to study. They glow with a faint white light. This light is a remnant of their former brilliance, a testament to the incredible processes that have shaped them. This is why we call them white dwarfs. Their faint white glow is a signature of their unique place in the cosmos, marking the end of a star's life cycle and the beginning of a new, quieter existence. Now let's talk about supernovae. These are some of the most powerful explosions in the universe. Imagine the energy of 1 billion suns released in an instant. That's a supernova. They happen when a star reaches the end of its life. There are different types of supernovae, but the kind we're interested in today involves white dwarfs. Sometimes, a white dwarf can steal material from a nearby star. This material builds up on the surface of the white dwarf. If enough material accumulates, the white dwarf can reach a critical mass. And when it does, it explodes in a supernova. These explosions are incredibly bright. They can outshine entire galaxies for a brief time. Now, back to LP40. 365. A fascinating celestial object that has captured the attention of astronomers worldwide. This white dwarf is special because it survived a supernova, an event that typically marks the end of a star's life. LP40, 365 was part of a binary star system, orbiting another star in a delicate cosmic dance. Over time, the white dwarf started pulling material from its companion star, a process known as accretion. This material built up on its surface, creating a dense layer of hydrogen and helium. But instead of a full-blown supernova, there was a smaller explosion, a less violent but still dramatic event. This type of explosion is called a Type IAX supernova, a rare and less understood phenomenon in the universe. The explosion wasn't strong enough to destroy the white dwarf completely, leaving it partially intact. Instead, it blasted the white dwarf through space at an incredible speed, turning it into a runaway star. LP40, 365 is now traveling at thousands of miles per second, a speed that is almost unimaginable. To put this into perspective, that's fast enough to travel from Earth to the Moon in just a few minutes, a journey that takes astronauts days. This high speed is a dead giveaway that it's a supernova survivor, a stellar remnant with a dramatic past. Astronomers continue to study LP40, 365, hoping to unlock more secrets about its origin and the nature of Type IAX supernovae. By understanding this unique star, we gain insights into the life cycles of stars and the dynamic processes that govern our universe. LP40, 365 stands as a testament to the resilience and complexity of stars, surviving an event that would obliterate most others. As we continue our journey through space, stars like LP40, 365 remind us of the incredible forces at play in the cosmos. Each discovery brings us closer to understanding the vast and mysterious universe we call home. Section 5. Properties of a survivor's speed, composition, and spin. LP4365 is a fascinating object. It's much larger than a typical white dwarf. This is probably because it absorbed some of its companion star's material. It's also spinning rapidly, about once every 9 hours. This is another clue about its violent past. The supernova explosion set it spinning like a top. But the most interesting thing about LP4365 is its composition. It's made up mostly of helium, with traces of other elements. These elements were forged in the heart of the supernova explosion. By studying the star's light, astronomers can learn about the conditions inside these explosions. Section 6. Unlocking Cosmic Secrets. The significance of LP40, 365. LP40, 365 is more than just a curiosity, it's a valuable tool for astronomers. By studying it, we can learn a lot about supernovae. These explosions are important because they seed the universe with heavy elements. These elements are the building blocks of planets, and of life itself. LP40, 365 is a rare glimpse into the aftermath of a supernova. It's helping us understand how these explosions happen, and it's teaching us about the life cycle of stars. It's a reminder that even in death, stars can create something new and amazing. Section 7. Future Explorations Unveiling More Mysteries. The study of LP40, 365 is far from over. Astronomers are still observing it. They're using powerful telescopes to learn more about its speed, composition, and rotation. They want to know where it came from and where it's going. And they're searching for other stars like it. Every new observation brings us closer to understanding these amazing objects. The more we learn about LP40, 365, the more we learn about the universe itself. Section 8. A Universe of Wonders, Reflections on LP40, 365. LP40, 365 is a reminder that the universe is full of surprises. It's a place of incredible violence and incredible beauty. It's a place where stars are born, they live, and they die. But sometimes even in death they can leave behind something truly extraordinary. The story of LP40, 365 is a story of survival, of resilience, and of the endless capacity of the universe to amaze us. It's a story that's still being written, and I for one can't wait to see what the next chapter holds. Section 9, A Continual Journey, LP40, 365's Future. LP40, 365 is now on a lonely journey through space. It's traveling at an incredible speed, leaving behind its former life, but its journey is far from over. It will continue to travel through the cosmos for billions of years. It will encounter other stars and maybe even other galaxies. And one day, billions of years from now, it will finally cool down completely. It will fade away, becoming a cold, dark cinder in the vastness of space. But its story will live on. It will be a reminder of the incredible power of the universe, and it will be a testament to the enduring nature of even the smallest stars.